existence, excuse me, uh, every moment of your existence has been mediated through. I mean, I just think about this. Every atom in your body, every atom in your body has been through the soil system billions of times already. I mean, the fact that you are not soil at this moment is a temporary condition, folks. And it's almost over. And I don't mean this talk. I mean your life. It's just a flash. I mean, most of the time you're soil and you come up around, hey, this is pretty good. Before you know it, it's like over. And I just think, where does it all come from? I mean, where does every atom actually come from that's been through yours, been through the soil billions of, maybe you don't know this, but it's all of those came from rocks. I mean, all of the atoms inside of your body were once inside of a rock. And maybe you don't know this, but rocks dissolve in water. So my goal tonight is, and we have a very short time, I think we have less than an hour. Is that correct, Erica, or is that about right?
We could go until about 8 or a little bit over if you
Okay.
need to.
I can. Well, I just spoke in Idaho for 9 hours straight. I'm not kidding. And it was like thrilling and exhausting. But I won't do that. I'll try and get to the stuff that matters. But there's some important things you need to understand about what soil is. And my goal here tonight is to get you to understand what it is and how it works. I'm not going to give you a recipe on how to do this. I want you to know, I'm going to teach you how to cook tonight, about what are the fundamentals, the basics of what it actually is. And most of you're master gardeners, you garden all the time, you're familiar with soil, you know how it smells, you know how it feels, all this stuff. But maybe you're wondering some of the details about really how it actually works and what it is. And what soil essentially is rotted rock. And I don't know if you know this, but here's a rock. I happen to have a rock right here. And rocks dissolve in water. And, you know, we don't live long enough to really get this, because we live 70, 80, 90 years if we're lucky, right? And so we don't really understand this. But in geologic time, rocks are actually very unstable at the surface of the earth. And they're made under the earth and under the heart of the earth at high pressure and high temperatures. And then when they cool at the surface of the earth, they crystallize into these things called rocks. And you can see these different colored crystals inside of that rock, because different rocks have different elemental minerals. The minerals are made up of the different elements in the earth's crust. And we're talking about the periodic table of elements. I mean, that's what everything is made out of. It's all made out of the elements that are in the periodic table. And all of those are contained mostly in rocks. And rocks dissolve in water. And I happen to have a little bit of water here right now. I'm going to put a little bit of water on here right now. Watch carefully. And put a little, see that? A little bit of water. And a tiny bit of that rock just dissolved. Really? A tiny, tiny amount. There's a little bit of hydrogen ion in this water that attacks the rock crystals. And when it does that, it actually weakens the rock, and the rock slowly starts to dissolve. And if you don't believe me that rocks dissolve in water, think here's some table salt, which is a mineral, right? And this particular mineral, if you put a little bit on your hand and lick it, you should do this tonight at dinner, or do it right now. And that's a mineral that dissolves very rapidly in water. And some minerals dissolve really fast, like salts, and some minerals dissolve really slow, like quartz, and everything else in between dissolves away eventually, right? And I mean, the first thing to dissolve out of a rock are the salts. And then the salts, they dissolve out and they move down in a soluble form, and they move down into the soil, and they keep going down. And pretty soon they get down to the water table, and that little bit of dissolved salt now is connected to the water table. And the water table is connected to the little river, and the little river is connected to the big river, and the big river flows into the ocean. And that's why the oceans are salty, because the salts dissolve out of the rocks and end up in the ocean. And the next thing to dissolve out of a rock is the molybdenum, or the calcium, or the potassium, or the phosphorus, or all the magnesium, or molybdenum. All that stuff eventually dissolves a rock, and it gets down to the water table, and it eventually ends up in the ocean. And that's why there's sharks. because those are what nutrients are. Nutrients originally come out of these rocks, and they all end up in the ocean sooner or later. But what soil is somewhere between all of the rocks being, all of the nutrients being locked up inside of a rock, or complete dissolution in the ocean. And somewhere in between those two extremes is this kind of temporary moment where the nutrients are still on the land, and they're still kind of locked up a little bit in some nutrients and in some minerals that are suddenly made available to plants, and then plants take them up. And then you eat those plants, and that's how it gets into you. Either you eat it, or you ate an animal that ate a plant, or your mom did. And that's how all these elements get inside of it. So that's like the importance of what soil is this inescapable fact that all of it comes from these rocks, and rocks dissolve in water. And that's fundamentally what a rock is. Now, different rocks, like here's a different rock here. All these different rocks have different colors. I mean, look at this one, completely different. So these are basically different nutrients are stored in the different colored rocks. And that's why there's different kinds of soils on the planet, because there's different kinds of rocks that they form from. And the precursors of the nutrients, the darker the minerals are, generally speaking, the darker minerals produce soils that are actually better for growing plants, where light minerals like this are mostly silicon dioxide, which is quartz. And quartz doesn't have a lot, and that's what the last thing to dissolve out of a rock is, the quartz. And where does that end up? It ends up on the beach. So if you want to see ancient mountain ranges that no longer exist because they've completely dissolved away, just go to the ocean and walk up to the water and taste the salts that have dissolved in the water, and pick up a handful of sand, which is the quartz, the silicon dioxide that's left over from those ancient mountain ranges. And everything else on land is going towards the ocean. But for this moment, here on the planet Earth, just for this moment in the history of the cosmos, here we are now talking about this, is this temporary moment where the mineral nutrients are sort of available, they're starting to fall apart, and they fall apart into different size particles. And the size of the crystals in these rocks determine the texture of the soil. And I'm sure some of you have taken enough soils in your master garden classes to know about texture, which is the percent sand, silt, and clay. Sand is a rock that you can feel. It's 2 millimeters down to 0.05 millimeters is considered sand size. Anything from 0.05 millimeters down to 0.002 millimeters is called silt size, which is much smaller. And anything smaller than 0.002 millimeters is called clay size particles. And the size of those particles determine the size of the pores in the soil. And the larger the pores are, the more well-drained and aerated soils are. And the smaller the pores are, the more the water holds, or the more the soil holds against the force of gravity, sort of like a sponge does, right? And plants, here's a plant right here, they need water and air all the time at their roots. And that's what loam is approximately equal parts sand, silt, and clay. And that's why loam is good. You probably have heard that. Oh, it's good. It's very loamy. It's loam because it has approximately equal sized parts sand, silt, and clay. And because it has approximately equal sized parts sand, silt, and clay, it has equal size parts of sand, silt, and clay sized pores, which drain well and hold water, which makes it good habitat. I mean, here, think about this. I don't know if you know this, but in a single pinch of soil, here's a single pinch, there are over 1 billion living organisms in there. 1 billion living organisms representing tens of thousands of different species, 99.99% of which we don't even know who they are or what they do, but we know they're there. Think about it. I dare you to forget that. I dare you to remember that. I dare you, before your head hits the pillow tonight, to go outside and in a private moment on your hands and knees, pick up a pinch of soil and just consider the fact that there are over 1 billion living organisms in this. If you get nothing else out of this talk tonight, if you get nothing else out of this talk tonight, if you can just intuit and feel the truth that soil is habitat. Soil is habitat by any measure. It's the most diverse habitat on the planet Earth in sheer numbers or mass of organisms. Okay. But I got to keep moving because I could just go down the rabbit hole on all these subjects. But we do have to talk about something else. We have to talk about organic matter. And that's what plants are. You know what? We could just cut to the chase. Do you want to know what the answer is? Doesn't matter what the question is. Do you want to know what the answer is? The answer is add organic matter. Because of what organic matter is. You do it 3 times a day if you're lucky, right? You add it. Why do we eat? What is organic matter? Well, I don't know if you know this, but what organic matter is, and I happen to have, look at this, a little dried rose here, right? This is a plant, right? What organic matter is whatever was once alive is organic matter, or is currently alive for that matter. And what this plant is made out of, maybe you know this, you probably studied just enough to know this. Maybe some of you have master's degrees in this or PhDs, but what organic matter is it's made of carbon. We are carbon-based life forms, right? And so are they. And where do they get the carbon? Plants, you know it's in the atmosphere, CO2. People think, oh, they breathe carbon. No, plants don't breathe carbon dioxide. They eat it. Plants eat the atmosphere. Now, I know, hang on, stick with me for a moment. This is all super important for the rest of our discussion because organic matter is the secret. It's the ticket, okay? Because plants eat the atmosphere. They take CO2 out of the atmosphere and they break it apart and then they put it together into rose petals and stems and grass and roots, right? Roots are organic matter and they're injecting roots into the ground. And in order for plants to take apart carbon dioxide and put it together into tissues like this requires energy input. And where does the energy input come from for a plant to eat the atmosphere? It comes from the sun. 93 million miles away, there's a ball of fire out there. A star is giving UV radiation to this planet. And plants have figured out a way to capture that energy from a star and use that energy by knocking a photon up. A photon knocks an electron into a higher orbital, it drops down, it releases a little bit of energy that the plant can use to do work. And the work of taking apart carbon dioxide and putting it together into a rose. And in this, and that the significance of that is in this carbon to carbon, these carbon to carbon bonds is the energy of the sun is in there right now from the time of photosynthesis, captured in those carbon to carbon bonds in chemical energy. And that's why, and that energy, the photosynthesis is the mother of all redox reactions, and everything else flows from it. Every blink of your eye was energy that was harvested from the sun by plants that lived in soil. Every beat of your heart is energy that was captured from the sun by plants that lived in soil. And you eat it to get the energy, literally get the energy. And I mean, here, look, here's a piece of paper, right? Paper is just, this was once a tree. And in this paper is the energy of the sun at the time of photosynthesis. And it's captured in it. And if I get this, if I rub this hard enough, I can get this to 451 degrees. And what happens at 451 degrees? We're gonna get it to work. That's a flame. This piece of wood is burning and giving off energy. And where did that energy come from? It came from the sun. And this, I can get this on fire. And now let this burn. And I can feel the heat from it right now. And you could see these flames, and you'll notice that the paper is going away. And where is this paper going to? Back to the atmosphere in the form of CO2. See what I mean? And it's giving off heat. And what's left over is something called ash. And what is ash? Ash are the mineral nutrients that were taken up by the tree. Look at this little bits of ash that are floating all over the place. You see this stuff? That's ash. Those are the mineral nutrients that were taken up by the tree. And the most of this plant is carbon. And it goes back to CO2, water vapor, and heat. And what comes out of every breath of your mouth? Look at CO2, water vapor, and heat. You're burning the food inside of you at a lower temperature. It's not 451 degrees in you. It's happening at a lower temperature because you have enzymes, because there's biota inside of you. In fact, the same bugs that are inside your gut are the ones that are inside of the soil. And what's happening in the soil is the same thing. So when you cut down a cover crop, or when leaves fall in the forest and they go to the ground, they're feeding the billions in a single pinch, because what do they need? They need carbon and energy from the sun, carbon from the atmosphere and energy from the sun. And that's what the billions in a single pinch of these bugs that live in the soil, that's what they need. And that's what you need, because they're inside of you. Look, there's a hole here and there's a hole back here. And inside of you is the outside world that's in this tube going through your body. And inside of there are the same biota that are inside of this soil. And the bugs in there, they ooze out enzymes which dissolve the organic matter at a lower temperature and release carbon, energy, and heat and ash. And the ash is what the mineral nutrients in your body. There's a skeleton inside of you that was made from calcium that was taken up by a plant. See what I mean? We have to talk about all that a little bit before I can even get to my slides. But I really want you to get a sense of this idea that rocks dissolve in water and those mineral nutrients get taken up by plants, and plants eat the atmosphere and get the energy from the sun to do it, to break the carbon and carbon bonds, to make tissues called tomatoes and peppers and eggplants and onions. They're all made from eating the atmosphere using the energy of the sun, and the mineral nutrients that they take up, very small amount of them. I mean, think about it. You burn wood in a fireplace for hours, and at the end of the night, you've thrown maybe 50 pieces of wood in there, and it's all gone. And what's left over in the fireplace is ash. And ash doesn't burn. Those are the mineral nutrients that were taken up by the trees. And those nutrients are then recycled with the next batch of plants. And that's what soil is. That's how soil works fundamentally. So I want to switch to some slides here. And we'll go into this just a little bit deeper. And I have a couple things I really want to show you. First of all, let me see if we get this advanced here. First of all, it's all about soil. Okay. I think I've made somewhat of a point on that, but I don't know if you know this, but there's only over 20,000 different named soils, and we're not going to talk about them all tonight. But just like plants and animals, oops, what happened here? Something happened here. There we are. Just like plants and animals, we've named all the 20,000 different named soils. And if you look behind me, you can see back here, these are some mounted specimens back here of just 30 of them. And so right underneath your feet right now is a soil that is probably characterized and named, and they all belong to one of the 12 soil orders. And I'm not going to go into great detail here, but look at, here's some soil, here's 2 of the 12 soil orders. This one's called an iridisol. What you're looking at here is a profile view. If you could dig a hole and look at the soil like looking at a wall, this is what this is. And this is an iridisol. And what do you think that means? It means dry. And do rocks dissolve in air? No, they dissolve where there's water. And so this is a dry soil. This is a desert soil. And if you look here, look at these plants that live in a desert environment. This right here is the thickness of the soil. That's it. The soil is only about 12 inches thick. And you look at this stuff right here. See this hard, kind of platey looking stuff here? You know what that is? Those are salts. So in this kind of environment, it rains only enough that it dissolves some of the salts, and they move down, and they go down to about 12 inches, and then it stops raining, and the soil dries out, and it leaves behind a little bit of salt. And it does that for 10 years, 1,000 years, 10,000 years, 100,000 years. And pretty soon there's a big layer of salt here. And the water never gets down to the water table. And so you get this soil that is not very well developed. And if you look over here on the right, this is called a mollisol. And a mollisol is one of the most agriculturally important soils that there is on the planet. And this soil, you could see this big, thick kind of chocolate cake, this thick layer here. You know why it's dark like this? It's dark because of additions of organic matter. And what is organic matter? It's carbon and energy. And what do the bugs need to eat? They need carbon and energy. So this is a very biologically active soil. And this darkness is this leftover organic matter that we call humus, which is actually a complex suite of compounds, but still it contains carbon and energy. And that carbon and energy is feeding the bugs, and the bugs are oozing out enzymes which are dissolved in the organic matter and making the nutrients available for the next generation of plants to be there. And so the more organic matter that is added into the soil, the better the habitat becomes for more plants. And the more plants there are, the more organic matter is added. And the more organic matter there is, the more plants there are, and the more carbon and energy is there. And that's what soil building is. That's why you're here right now, is because that happened. And every beat of your heart was harvested energy from the sun that lived in living soil, and probably these kind of agricultural soils. In fact, our entire technological existence, like this moment that we're on Zoom right now, how does that even happen? That happens because somebody invented agriculture. And when the invention of agriculture is what led to surpluses, and those surpluses could be used for specialization, and people could become specialists. And that's what the Industrial Revolution was. And then the information revolution that we're experiencing right now in this technological society is basically fundamentally tied directly to agriculture and soil. And all of the comforts that you know are coming from that fundamental fact that there is soil, and that energy is harvested from the sun, and carbon from the atmosphere, and everything else flows from that, and it can't really overstate it. So here's a iridesol and a mollisol. And it's going the wrong direction. Sorry. Look at this. Here's another couple of soils. An iridesol. Here's an iridesol again. An inceptisol. 1/3 of the Earth's ice-free surface are these kinds of soils. Only 10% of the Earth's ice-free surface is suitable for growing crops, and it's all in production. Look at this. What you're looking at here is a map of the soil orders of the world. This is where they're distributed, and they're not evenly distributed, and it explains a lot. And if you look at the United States here, if you look at this, you can see that there's a lot of the mollisols. See, they're in green here. They're shown in green here. 21% of our landmass is in mollisols. That's why we're a rich country, because we have an advanced agriculture, which leads us to have an advanced industrial nation. Worldwide, it's only 7%. So that's all you really need to know, is you live in a country that has 21% of its land mass is mollisols. Worldwide, it's 7%. And in most countries around the world, like in these areas of the world, these are where the iridosols are and the inceptisols are. And really, this is what you're really looking at here, is a map of political power. They who have the good soils have the thermonuclear weapons. I mean, look at this map. Tell me, where else on this map do you see as many mollisols as we have here in the United States? Right here in Russia. What do you think this whole conflict is about? And it's all about soil. You might be thinking, oh, aren't the tropics good? Actually, the tropics are terrible soils for agriculture, mostly because it's so wet and so hot there that all the nutrients have washed out of those soils and gone into the ocean. Where we're in this temperate region where it's warm and sunny enough in the summer that we get lots of growth, but it's cool and wet enough during the winters that a lot of that organic matter doesn't go away and those nutrients hang around. It's not so wet that the nutrients wash away. And if you look up here in the northern high latitudes, these are the frozen soils up here. So I'd love to spend more time on this image as well, but we got to keep moving. So here's an oxisol in the tropics. And what this is mostly just rust. What's left over after rocks dissolve away, and what's left over is iron oxide. And we see these red soils in the tropics. And if you've ever been lucky enough to go to the tropics, you've seen these red and yellow soils, and they're mostly just oxides. And they're not particularly good because they don't have a lot of nutrients. Because where are the nutrients? They're out in the ocean, and they're becoming sharks. All right. And here's a spottisol on the Oregon coast. These are sandy soils that are formed from old sand dunes. Here's an entisol and septisols. Bottom line though, soil, what if you look at this, this is real soil here. Soil doesn't come in a bag. Soil forms over time from rotted rocks and accumulations of organic matter over time. And soil is sculpted by the energy of the sun. I don't know if you can see this right here where I have this cursor. You can see this little crack right here. What that was an old root. A root grew into the soil and then pushed the soil apart because it got bigger. Its carbon and energy was literally got bigger using the energy of the sun to sculpt a bigger pore. And then that plant died. And what happened to the root? It decomposed and went back to CO2, water vapor, and heat. Whence it came, left behind a little ash. But now there's this big pore here, and large pores drain under the force of gravity. And so large pores drain under the force of gravity, which actually bring air in. That's what drainage does, is it brings in air. I mean, think about it. When a water droplet is going down into a wormhole and it drains, what's being sucked in behind it? There's a partial vacuum when that droplet goes down in there and being pulled down by gravity, and that's pulling in the atmosphere. So when the soil is draining, the soil is breathing, because these billions in a single pinch, they need to breathe oxygen just like you do, for the same reason you do, to dump electrons onto, to create ATP, to build their tissues, to build how you're made. And so because roots go down into the ground and leave behind a casting of those roots, when they completely decompose, they leave behind large pores, and large pores mean the soil is more well drained and more well aerated, which makes it better for soil biota, which makes it more efficient to decompose organic matter, which makes it so there's more nutrients being released so that more plants can grow there, so more roots can go down and sculpt the soil and make the soil better for plants, so more plants go there. And that's carbon and energy being injected into the system. And that's what a mollisol is, and that's what soil building is. And that's what you're trying to do in your garden. That's why you grow cover crops, is to inject carbon and energy in the roots and then cut the plants down and feed it back to the soil, which makes the soil more robust and more biologically active, so that the next generation of plants will grow better and add more organic matter. So bottom line, soil is habitat, a billion in a single pinch. And what you're doing is you're feeding them. And the more you feed them, the more plants will grow there. And that's why the answer is add organic matter. So look here, I mean, this tiny little, here's a little crumb of soil that's a tenth of it, like a half a millimeter wide by a millimeter tall. And look what's in here. Here's pieces of sand, pieces of silt, and pieces of clay. Each one of these pieces of sand is a different kind of rock that has different mineral nutrients in it, that's releasing nutrients into this ocean of water. And this little ocean of water right here is, I mean, you've all taken baths, I know, But you know how a little gap of water will hold between your fingers? Small pores hold water against the force of gravity. Large pores drain under the force of gravity. And you can see right here is a large pore that's drained under the force of gravity. And that used to be a root there. And that root went in there and got bigger and pushed these pieces of sand apart. And now there's a water-filled small pore and a well-drained, aerated large pore. And that's really what you're trying to do in gardening. Is you're not really gardening, you're managing space underground. You're managing habitat for microorganisms. You're managing microbes, really, and the plants come along for the ride. And what do these microbes want? They want air and water. And that's why you want a well aerated but water storage. And look, in this little bubble of water here is a sea serpent living in here. And this thing is eating these things, and this thing eats the poop of those things, and these things are waiting for this to die. And inside of between these three pieces of sand is in a complete ecosystem. And way up here, look at this root here. This root is leaking out sugar water. And this water right here is a completely different chemical signature than this water right here, which has ciliated protozoa in it. And down in here, this is where the bacteria are eating old organic matter. And up here is the lion on the Serengeti. And all of this is happening in a thing that's smaller than if you broke off the tip of your pencil. That's what soil is. Soil is habitat. It's the most diverse habitat on the planet. And once you get that, and once you understand that the diversity of habitat is what leads to the diversity of organisms, which allows for the diversity of processing of carbon, energy, and nutrients, which makes a better soil for growing plants. And that's what you're doing. Soil is a living thing. If you get nothing else out of this talk, if you can internalize this idea that soil is a living thing, it's not a chemical sponge. And what do living things need? They need to eat. And what do they eat? They eat organic matter. And why is that? Because organic matter is carbon from the atmosphere and energy from the sun. The same thing you need is what the soil needs. All right. Let's relax just for a second. Let me catch my breath, get a little water. All right. So let's review really briefly here. What is soil? Soil is rotted rock, decomposed organic matter, and space. You're really just managing space. And what's in the space is determined by the size of the pores. And what you want is a wide pore size distribution. You want big pores, medium pores, small pores, tiny pores, and super tiny pores. Because big pores drain under the force of gravity, and small pores hold water against the force of gravity. So what is soil? Soil is minerals, air, water, and decomposed and organic matter. Okay, that's what it is. Those four things: organic matter, minerals, air, and water. And we've talked a little bit about what these rocks are, right? And just briefly, we're going to go in a little closer. And here's like a little pie graph. And what soil is, it's about half of it. Half of this thing right here that I'm holding up in the camera here, half of this little chunk of soil right here is space. And that space either has water or air in it, depending on the size of the pores. Then the rest of this thing is either sand, silt, and clay-sized minerals. And then there's this little slice here called organic matter. And 5% organic. You should all get a soil test. I mean, if you're serious about gardening, you've got to know how much organic matter you have in your soil. And you've got to track it through time. And you shouldn't be going down. You should be either maintaining organic matter or building organic matter. And it's not easy to do. You got to add a lot of compost, because compost mostly goes back to CO2, water vapor, and heat. And some of it sticks around and gets stuck in the clay, and it becomes part of the soil, organic matter. And if you have 5% organic matter in your soil, you're pretty good. You don't really need to add any more than that. And you need to get a soil test to find out, because you could just keep adding it forever. But you know what? There's a certain point where it doesn't really behoove you to do that. 5% organic matter doesn't sound like very much, but it's actually quite a bit. So get a soil test and find out. But we'll get back to organic matter in just a second. So here's a rock. What is a rock? A rock is a collection of minerals, and you can see the different colored minerals in here. And what are minerals made out of? Minerals are just a collection of elements, right, from the periodic table. And the dark elements are actually more, they are more easily dissolved. These dark crystals are more easily dissolved than the white ones because of the temperature at which they cooled at, and et cetera, et cetera. But the dark minerals contain most of the important nutrients that are needed for biological systems. Things like molybdenum, things like iron, things like manganese and magnesium, and potassium, those are all super important things. And so the darker minerals are actually the better nutrients contained in them. And so they're the first thing that dissolve out, and pretty soon that dissolves out. And when that dissolves out, it leaves behind all these red things. And then the whole thing kind of falls apart into sand-sized particles. And these white things, these will eventually become beach sand. So if you have a granite countertop, you should go there and just look at it tonight and just think about that. Eventually, that granite countertop is going to completely dissolve away sooner or later. And all the mineral nutrients that are in there are either going to hang around in the soil and be part of living biological systems and living and dying and living and dying and living and dying and living and dying and being part of the soil, or eventually they're all going to end up in the ocean and become sea life and sharks and fish and octopus and stuff like that. And that's where those mineral nutrients, that's where they go. And this is where the nutrients really are stored, or in rocks. And then these different size particles, sand, silt, and clay. All sand is, and you know what sand is, it's a particle of a certain size that you can actually feel. But sand is just a rock, okay? It's just a rock that is a certain size. Silt is just a rock. It's just a smaller one. Clay, I don't know if you can even see this, the smallest pixel on the screen is actually too small to represent its size compared to sand and silt. Clay is a different thing, and we're going in now. This is really how soil works, okay? How it stores nutrients. So pay attention. I know it's 7:45 here already. It's getting late, but this is the reason you're alive, and I want you to pay attention right now. What clay is formed when rocks completely dissolve and then recrystallize at the surface of the earth, not down in the melt, but at the surface. So when rocks are very unstable at the surface of the earth, and they dissolve, and then they recrystallize at normal surface temperatures and normal surface pressures. And these crystals, imagine it's a crystal, it's like a plane growing, right? And as that plane grows, it gets longer, and it's a thin sheet, and it can only get to about 0.002 millimeters before it breaks in half. And then it grows and it gets to 0.002, and then it breaks in half because it's not stable at any larger size. And that's as big as a clay crystal can get. And that's why these particles are so small, is because they're formed in the soil. And they can only get so big, and they stack up these little sheets. They stack up like in a leaf, like the pages of a book. And they have enormous surface area, and yet they're really small. Kind of hard to get your head around that. Tiny little particle, giant surface. Imagine the surface area of all the pages in a book. If you could add those all up, but imagine the book only being 0.002 millimeters and having all these tiny layers. That's what clay is. It's not a rock. Nothing lives, nothing lives inside of a rock. Sand is this giant rock. Silt is a pretty big rock. Clay is not a rock. It's a secondary mineral that forms at normal surface temperatures and normal surface pressures, and it's the product of dissolution and recrystallization. Clay is the reason for the season, and it's clay. Clay is what stores the nutrients. That's where the nutrients aren't stored on sand. Nutrients aren't stored on the surfaces of silt. They're stored on the giant surface areas of clay minerals. And we're going to go in now. Look, rocks dissolve in water. And when they dissolve out, what's dissolved out? Look at nutrients: silica, aluminum, iron, magnesium, potassium. That's what's dissolving out. And when they recrystallize into these sheets of silica and aluminum oxide, the four most abundant elements in the Earth's crust are oxygen, believe it or not, oxygen, or that's what rocks are mostly made out of, is oxygen. Where do you think the oxygen came from? Oxygen, silicon, aluminum, and iron are the most four most abundant elements in the Earth's crust. And those are the things that form these sheets. And when a rock dissolves, hang on now, we're going in. When a rock dissolves, this is what's dissolving out of the rock. There's silica and aluminum, and silica has just a certain amount, a certain size, and a certain charge on it that it forms a bond, a covalent bond with four oxygens. Hang in there, okay? Hang in there. This is the reason you're alive, all right? Silica tetrahedrons are formed, and they are floating down, and those are the building blocks of that crystal, silica tetrahedrons. Similarly, aluminum octahedrons aluminum has a certain size and a certain charge that forms covalent bonds with oxygen, or in this case, hydroxyl groups. This is the aluminum octahedron. And these are the building blocks of that crystal. So dissolving out of the rocks are silica and aluminum that form these crystalline structures of silica tetrahedrons and aluminum octahedrons. Hang in there. Okay, look, here's the silica tetrahedral plane. And there's another, this is the edge of that crystal. And as the silica tetrahedron, as the silica dissolves out of the rock, it forms on the edge, and this thing goes building like a tinker toy. And it's a crystal that's growing. And it grows, and where there's more water, there's more dissolution of minerals, so there's more clays. Here's the aluminum octahedral sheet. Here's another silica tetrahedral sheet. This is called a 2-to-1 clay. Now look, this whole thing is called the layer here, and there's another one, and another one, and another one, another one. They stack up, and they can only stack up to about 0.002 millimeters before they fall over. Okay, so that's what clay is. It's like a book as opposed to a brick. And there's all those layers in there. And it's made up one atom at a time as that crystal grows and gets to about 0.002 millimeters before it breaks. Okay, so now let's just examine. So here it is. So here is a silica tetrahedrons. Now here's something you need to know. Certain rocks have other elements in them depending on the color of the rock, right? And so the clays that are formed from some rocks are different from the clays that are formed from other rocks. And not all clays are equal. Some clays have more negative charge. Write this down. Soil is a negatively charged thing. Write it down. Soil is a negatively charged thing. Okay? And it's negatively charged because of what happens on clay. So here's the source of that negative charge. And then I'm going to tell you why that negative charge matters. So hold on. So remember the silica tetrahedrons and the aluminum octahedrons? As it turns out, there are other elements that are dissolving out of the rock that are in the soil water solution. And as it turns out, some of them have almost the same size and almost the same charge as silica and aluminum. Things like iron and things like magnesium have almost the same size and almost the same charge, and they get into the clay crystal as impurities. And when I say almost the same size and almost the same charge, there's a little bit of a negative charge left over. It doesn't completely satisfy the charge of the tetrahedron, the octahedral ordination. And so now look here, here it is. Here's a layer of clay at a tiny, we're zoomed in closer than you could ever see, even with a microscope. And things like iron can substitute in for the silica at the time of recrystallization. And look what happens. There's a negative charge propagated to the surface. So because there's iron substituted into the crystalline lattice work at the time of recrystallization, there's now a negative charge on clay. That doesn't happen on sand. That doesn't happen on silt. Okay? And the same thing happens. Magnesium can substitute into the aluminum ordination in the crystal at the time of recrystallization, more negative charge. So the more negative charges there are, the better the clay. And why is that? You know what sticks to negatively charged things? Electrostatic charge, positively charged things. And you know what the charge on most mineral nutrients is? Positive. Calcium, magnesium, potassium, phosphorus. All those things have positive charge and they're in solution and they stick temporarily like a balloon stuck to a wall temporarily, and they don't wash away and go into the ocean. They're stuck there because clay is a negatively charged thing because of isomorphic substitution in the crystalline lattice work at the time of recrystallization. Whoa. That's why nutrients, that's why you put fertilizer on your soil, is to put those charged, those nutrients onto the negative exchange complex of clay. And the higher the number of negative charges, the more nutrients can be stored. And that's why some soils are better than others for agriculture, because they come from darker rocks. The soils form from rather than lighter rocks, because this has more ability to make good clays. Wow, okay? And this is the reason you're alive. Every atom in your body was once stuck in the negative exchange complex of clay, and then a plant took it up, and that's why you're here. So let's look at this. Isomorphic substitution on the secondary mineral called clay. Look at, here's clay at 100,000 times magnification. 100,000, look at it. It's not a rock. It's not a piece of sand. It's not a piece of silk. It's been built up by elements, excuse me, one atom at a time, and they can only get to 0.002 millimeter. Look at the layers and and there's net negative charges all over this thing. And when you get a soil test, you may have heard of the cation exchange capacity, the CEC of a soil. The CEC of a soil is how much negative charge it has. The more negative charge a soil has, the more nutrients it can store, and the more energy and carbon it can harvest from the atmosphere and from the sun. And that's why land costs money. And better land costs more money because it can capture more energy from the sun and more carbon from the atmosphere. And so that's why cheap land is no bargain. Look, here's clay. Look at negative charge due to isomorphic substitution. Second mineral called clay. Look at net negative charge due to isomorphic substitution. These are clays. That's clay and has a net negative charge on it. Look at the surface area. Look at the porosity of the soil. This has like 80% pore space. And where is the activity in soil? Is in the pores. Has net negative charge. Look at net negative charge due to isomorphic substitution. Net negative charge due to isomorphic. Look at this. Look at this is clay. There's a net negative charges all over that due to isomorphic substitution in the second mineral called clay. And that is how nutrients are stored in soil. All right. So net negative charge due to isomorphic substitution on the secondary mineral called clay is the reason that you could put fertilizer on. I mean, look at this. Here's a clay. You can see it now. Look what's stuck there. Calcium. Look at this clay. Calcium, magnesium, potassium. This is what fertilizer is. You put fertilizer in the amounts you want to grow the plants you want. You put that in the soil and it's stored in the soil until the plant needs it. And then the plant can get those nutrients because it didn't wash away. All right. All right. Turns out there's one other thing in soil. You have to guess what it is. One other thing in soil that has twice that negative charge of the best clays. And that thing is organic matter. And so you might be saying, wow, we were just talking about all this clay and stuff. What about organic matter? When you add organic matter, you're adding negative charge because organic matter itself, the black stuff, has net negative charge and a giant surface area. You might be saying, well, why don't we just add clay? From whose dead cold hands are you going to get the clay? Because that is the value of the land. But you can add organic matter, and the easiest way to add organic matter is to grow it. And that's what a cover crop is. When you add organic matter, I'm skipping ahead here, you end up with this random molecule that's black. Because it's random, it doesn't reflect back any of the electromagnetic spectrum in a specific color. And this has net negative charges all over it. So the answer is add organic. If you have a low CEC soil, if you have a sandy soil that doesn't have a lot of clay in it, The answer is add organic matter because it increases the cation exchange capacity, right? Look, here's a plant. Plants, part of the plant is underground. Think about this. Here's a large pore, a medium pore, and a small pore. Currently, it's occupied by carbon and energy, and that will eventually rot away. What will be left behind? A large pore, a medium pore, and a small pore. And so plants are sculpting the soil using the energy of the sun and carbon from the atmosphere to make the soil better habitat for plants. But look, plants, look, they eat the atmosphere, carbon dioxide, and they evaporate at their leaves, which drops the pressure and that pulls water in. So plants, because they're evaporating their leaves, they're sucking water in at their roots. And along with that comes minerals and nutrients. Now, I don't know if you know this, but plants breathe at their roots, and that's how you can drown a plant. Who here has drowned a plant? If you overwater a plant, you drown it because they breathe oxygen at their roots. And how do they get oxygen in their roots? By having big pores. In fact, that's what the roots are partly doing, is they're creating a place for water to drain through this large pore, and then that'll bring in oxygen so they can breathe. All right. So zooming in, this is how the plants get the nutrients. And this is the last slide that I really want to focus on, okay? So hang with me. Look, here's a plant. Look, here's a root. Look, here's a tiny root looking in. Here's the tiniest root hair you never saw because it's so small you can't see it with the naked eye. And look at the little tip of the root hair, tiny. And where's the tiny root hair? It's in the tiny pore. What's in the tiny pore? Water, because water is held in the small pores. And look, here's a piece of soil. Look, it has negative charge on it due to isomorphic substitution, the second mineral called clay, or it's some sort of coatings of organic matter, but there's negative charge on it. And look what's stuck to it, positively charged nutrients. Now, plants breathe at their roots and they exhale CO2 at their root hairs. And when CO2 dissolves in water, and you all know this, if you ever open a can of soda and the bubbles come out and it tastes a little bit acidic, that's because CO2 dissolves in water. And when CO2 dissolves in water, it forms carbonic acid. And that acid is hydrogen ion, which is more strongly absorbed to the negative exchange complex than the nutrients are. And that's how the nutrients are kicked off. So when the plant exhales at its roots, CO2 goes into the water, which acidifies the water. And that acidity actually removes the nutrients because the hydrogen ion is more strongly absorbed to the negative charge than the calcium is. And so the calcium gets kicked off and it flows into the root, and then it becomes part of the plant, and then you eat it, and that's why you have a skeleton in you. And every atom in your body has been on the negative exchange complex of clay organic matter, and as it has done billions of times already. You see what I'm saying? And check it out. You could look at this. Look at this. Look at these images. Zooming in. Look, there's a root, the tiniest roots. Look at, there's a big pore here created by this large part. So it's breathing here and it's exhaling at these little root hairs. And those root hairs are mining the nutrients because they're acidifying the water. And that's called ion exchange. And that's the reason there's life on this planet Earth, is multicellular life, is because the excess nutrients are not washing away and going into the ocean. And those nutrients, they do things. Look at molybdenum, chlorine, chloride, calcium, silica. All these nutrients have functions in a plant. And then we eat them and they have functions in us. And then we all die and we go back to the soil. And this whole thing is being driven by solar energy. It's almost like we live in a giant solar system. You know what I mean? And so all of this is happening because we are floating around on a rocky planet with liquid water around a sun. And the energy, all of the energy comes from that. And man, it's 3 minutes past 8. And I probably better stop, or else you're going to give me the hook. And I'd be happy to take some of your questions if you have any.
Wow. Take a breath there, James.
Oh, yeah.
You're
I
you're
did
a
it for
little
9 hours last week.
you're slightly passionate about this topic.
It's all about soil.
Yeah. Well, we did have a question come in asking if you could talk a little bit more about cover crops. Maybe we end with that.
Well, cover crops, now you know why though. See, it's the reason you go cover crops. There's a number of reasons. Of course, one of them is just to cover the ground in the rain, to keep the rain from eroding. Because you know what the first two things that are lost in soil are in erosion? Clay and organic matter. Clay and organic matter are the things that have the charge. And when you lose clay and organic matter, you're losing the fundamentals of what give that soil the properties to be able to store nutrients. So you want to protect the soil in the winter with some sort of cover, and you may as well grow something that's beneficial and outcompetes the weeds. So it outcompetes weeds. But what is a plant? It's roots. And those roots are injecting into the soil and making and releasing carbon and energy and nutrients into the soil. And they're making it more drained, more well drained over time. And then when you cut those cover crops down in the summer, they rot and they release carbon, energy, and nutrients to the soil, which then recycle those carbon, energy, and nutrients for the next generation of plants that are called your garden plants. So whatever you put on is better than nothing. You know, I mean, legumes fix nitrogen from the atmosphere. So if you grow a legume cover crop, you're actually getting nitrogen out of the atmosphere and fixing it into the tissues of those plants. And then when you cut those plants down and they biodegrade, you release nitrogen into the soil that wasn't there before. So instead of using fertilizer, you can grow your fertilizer. So there's a wonderful book called Growing Cover Crops for Increased Profitability or something like that from Western SARE. And it's got these charts in there. It tells you all the different kinds of cover crops that you can plant for different purposes. And I'd be happy to share that with you. Maybe you can send it out or something. It's called Growing Cover Crops Profitably, the 3rd edition. I saw a question there about, is it too late to plant cover crops? No, because we got this really dry, warm fall. It's time though. I'm putting in my cover crops next Tuesday. And so get the ground prepped, put on the cover crops, and let the rain come. And sometimes if it's too wet though and too cold, it's too late, and it isn't right now. So anytime the beginning of October into the beginning of November, as long as the ground isn't too wet and cold, you should get your cover crop seed in for sure.
Great.
Yeah.
Great, thank you. So one person's asking, when they are weeding, should they not pull the weed out by the root? Should they try to leave the
Great
root
question, because now you're thinking like, you learn, oh my God, A+, whoever that is, gold star, because you thought, wow, maybe I should leave the roots because the roots are super important. Yeah, they are. Now, some weeds, if you just cut them off, they grow back. So you got to know your weeds. But some weeds, you cut them off and they die. Same with tomatoes. You know, leave the root ball. Just cut them off. Try and disturb the soil as little as possible. Because when you disturb the soil, you're breaking up all that structure, all those large pores. The large pores are the things that are most vulnerable to disturbance. And when you rototill soils, you lose the large pores. So you lose the drainage and the aeration and the oxygen coming in and feeding the soil, or oxygenating the soil. So many of your actual crops from the summer, you can just leave the root ball in and cut it off the surface. Lots of weeds you can do that with too, but like I said, sometimes they grow back. So you got to know which.
Okay, and we'll just ask one more. There's someone who's asking if you can quantify the carbon that is sequestered in plants and soil.
You know, I don't have that information at my disposal right now, but that is how carbon is sequestered in soil, is in the form of organic matter. So you know, a lot of people think trees are you know, plant trees, but you know what? Trees, not all soils are benefiting from having trees. Some are benefiting from having grasses or sage. So not all, you know, you don't just want to get on the, like, everybody wants to plant 1 billion trees, but maybe some places it's not appropriate for the soil types and for the plants and animals that live there. So grasses are very competitive with trees because most of the plant is underground. I mean, a large portion of grass, I mean, that's why you can mow the lawn, because most of the plant is underground and it just keeps sending up like an antenna, the new stuff. And that's what grazing is. And grazing makes for more aggressive roots. So properly grazed grasslands actually sequester a lot of carbon. And so, you know, vegans don't want to talk about that a lot. I'm not a vegetarian or vegan, but I do eat a lot less meat because I understand the impact of meat on ecosystems. But wisely produced, you know, it's, I mean, animals are a part of the system. You can't take them out. That's part of, that's why there's mollisols, is because bison ate grass and made mollisols because they come from grass soils. So I don't know if that was much help, but I do want to share one slide with you still, if you don't mind. And let's see if I can find that. And it's right here. It is. This is a little bit of a plug here. I do sell these shirts. Yes. And 100% of the profits of these shirts goes to supporting my student farm and my interns specifically. So won't you please go to soilforward.org and order one of these shirts? They're 100% cotton, and I have them in gender neutral and in form fitting, I think is what we say now. And I also have them available in Klingon and in Vulcan. So if you know any Klingons or Vulcans looking for a t-shirt that says soil on it, because even Klingons and Vulcans need soil because they eat. And what do they eat? Carbon and energy. And where do they get it from? Plants or animals that are harvesting it from the atmosphere and from the sun. So had to throw that in there. Please, won't you support the kids? The kids, it's their future. We're done. They inherited this world. And I've got to tell you, I get 70 of them every Thursday night, and they're just excited to farm the student farm. And they're learning how to do it organically. And they're learning about cover crops. And they're learning about carbon and energy. They're learning about composting. And they're taking classes in organic agriculture that didn't exist before there was a student farm at this university. The reason there's a student farm at this university called the OSU Organic Growers Club is because 3 students complained and said, why aren't we learning anything about organics? And they said, why don't we just start our own damn farm? And they did. And I went to their first meeting, and I'm still doing it. And those same kids now, the generations have gone by. Over 200 students have been interns at my student farm and were paid through the sale of fruit and vegetables with no support from the university, other than that they don't try and throw us off the land anymore. And these t-shirts. So won't you please buy a soil t-shirt? Christmas is coming.
Wonderful, James. Thank you so much. Your passion is infectious, and folks are indicating that they've learned a lot and have really enjoyed your presentation. Thank you for spending the evening with us, and we hope to cross paths with you again.
Well, I'd love to come up there and do 9 hours with you sometime.
Excellent. Good night, folks.
Good night, everybody.